Okay, so here's where we were last time. We were talking about triple integrals, and I almost finished the section, but just not quite. I just wanted to talk a little bit about, now that we've drawn this figure, right, the last thing we did was talk about how to go about drawing this figure, given as it was just in terms of, the 5 planes that it is the intersection of, or that it's bounded by as the intersection. How do we go about slicing it up? So again, you have 6 different choices, 6 different ways that you can order the differentials. There were 6 different ways you can slice. And I just want to make the observation that really most of them are bad. Right? So, for example, if you start by slicing perpendicular to the x-axis, in other words, if you do your dx on the outside, look what your slices look like. You have these little slices over here, like that, and then your slices get bigger as you move, further in the x direction. Then eventually you hit that edge. Right? And your slices don't look terribly, terribly different. But what's important is that the plane that defines them has changed. So for the first little while, it is this plane that defines the top edges of those slices. But later on, it's this plane that's defining the top edges of your slices. Right, so the easiest way to see this, of course, is that we slice through a corner, or in this case, in fact, a full edge. So that's a good reason not to do your dx slicing first. So along those same lines, what happens if you do your y slicing first? Well, you slice through that corner. Right, so your slices are looking like this. Everything seems to be fine and dandy until you hit that corner. Whoops, color change. Once you hit that corner, your slices look fundamentally different. So the bounds on, if you were to insist on doing your y slicing first, your x and z bounds would be different over here than they are over here. And so again, you'd have 2 separate intervals. So both of those are highly undesirable. On the other hand, if you do your z slicing first, no problem. Slicing perpendicular to the z-axis. Oops. You don't slice through any edges, don't slice through any corners, no problem at all. Everybody happy? Everybody see the point here? Okay, now, which of these is better after that? If you, since we've agreed we're doing our dz slicing first, should I do dx and then dy, or dy and then dx? In this case, it doesn't matter because this is a rectangle, right, as it turned out. But suppose it had been a little different. Suppose that the equation of, this plane, the plane that defined that edge, suppose that plane had been tilted a little bit. And let's see here. I'm going to let me redraw like this. So suppose it had been tilted instead of straight back that way. What if it had been kind of angled like this and then tilted back? Right? So that our solid now looks like that. Well, still we want to do our z slicing first. Okay, let me go ahead and get rid of the oops. Get rid of all that stuff. Okay, z slicing first, so our slices are going to look like that. And now should we do our x slicing first or should we do our y slicing first? And I suggest that because this edge here is now kind of turned in that way a little bit, right? This is no longer parallel to the x-axis. If we were to do our y slicing next, note what our y slices would look like. Our y slices would look like this, right up to the point where I would hit that corner. After which they would change. Right? Specifically, instead of being determined, the upper bounds of x being determined by this edge, it'd be by that edge. So that's a bad choice. Okay. On the other hand, oh man, hit it again. How did I do that? On the other hand, if we do our slicing in this order, do our x slices of our z slices, no problems. Okay, so anyway, I just wanted to talk through those scenarios in terms of the slicing. You know, once you have the picture, you can start thinking in terms of your slicing options. And again, try to avoid corners, try to avoid edges. Okay, so that's all I wanted to say about that section, 5.5. We're moving on now to 5.6, change of variables. Y'all have actually seen a version of change of variables already. They just don't call it that. In single variable calculus, they call it the substitution rule. Let me remind you of the substitution rule. Now, y'all know, how to do substitutions, but this is a statement of the substitution rule that this antiderivative is equal to that antiderivative. And the way you think about it, typically, is that if x is g of t, we think of making the substitution dx equals g prime of t dt. Right? That's kind of how business is done. That's how you do it. And of course, you can go either way. You can rewrite this as that or that as this, depending on where you are and what's convenient. Okay. I want to view this as a statement about integrals. Here's the substitution rule for integrals. All this says is once you have done your substitution, once you've written one of these in terms of the other, don't forget that the bounds have to change correspondingly. And the way I like to think about this is what that says. A, that subscript, or that lower bound of A, that's a value of t. So if t is equal to A, notice that means that x is g of A. When t is equal to A, plug that in, x becomes g of A. And that's one way to think of it. Okay. All right. So this is a version of change of variables. This is a one-dimensional version of change of variables. So what I'd like to do is I'm going to give you a slightly different point of view on how to think about this, what we've formerly known as the substitution rule for integrals. A different way to think about it, and then it's, as usual, as is often the case, the different way that I'm going to give you all to think about this is the way that's going to generalize nicely into the multivariable context. Okay, so here's the different way I want you to think about it. This formula, x equals g of t, don't think of this simply as an algebraic thing, as just algebraic symbols that we write, and so that we can plug in and manipulate algebraic, purely algebraic process. Let's think of that as, a function that we can draw a picture of, such as this. So there's our function g. And x is the output, t is the input. This says x is g of t. Okay, so if you have an interval from a to b on the t-axis, plug that into this function. Well, let's see. When t is equal to a, plug that in, you get g of a for your x. Right? Likewise, when t is b, you get g of b. So the punchline, this interval from a to b on the t-axis, the image of it by this function is the interval from g of a to g of b on the x-axis. And what these integrals then say, if you look down here at these integrals in the substitution rule for integrals, notice that there's two integrals, one on the t-axis, one on the x-axis. The one that's on the x-axis is an integral from g of a to g of b. This integral from g of a to g of b, that's an integral on the x-axis on the image, the output set. Whereas this integral over here on the t-axis from a to b, right, is an integral defined on this original integral. So the substitution rule, you can think of that as, well, look, we're literally taking an integral on the t-axis, we're looking at its image over on the x-axis, and we're relating an integral that happens there and an integral that happens there. We have a domain and the image of that domain, right? Both as being, we're having integrals defined on both of those intervals. Okay. All right. Now, what are we going to do? What does that have to do with how change of variables works, or how the substitution rule works? So, again, thinking of this as a function, right? How would I define an integral on either one of these sets? Well, of course, my usual process is I slice this up into pieces, and well, I note that if you have a little piece here, some little piece of size delta t, however big that is, you can talk about, well, how big is its image? Its image is a little piece of the x-axis. Very naturally, we might want to call that delta x. Right? So the process of slicing up this domain into little pieces, using which we can write a Riemann sum, aka an integral, gives us a process of slicing this up by which we can write a Riemann sum, aka an integral. Right? So creating an integral here gives an integral here. Most of this is just a matter of recopying then. Anywhere you see that you have anywhere that you see you have an x, well, just plug in. Let's see, where's mine? Here it is. Anywhere that you have an x, I missed. Anywhere you have an x, just remember x is g of t. Most of your expression simplifies like that. X is g of t, so just plug that in. Right? There's just one other little detail that we have to worry about, and that is we have to relate delta x and delta t. Right? What is the relation? I can't just say delta x equals delta t. They aren't equal. Right? This little piece gets stretched out in some form or fashion, depending on what that function is. Right? So delta x is going to be some kind of stretched out version of delta t. So the question is, what is that relationship? This is an application of derivatives. If I want to know the size of this as it relates to the size of this, let me just observe that each one of these sizes I can think of as a change. So what I'm asking here, by what factor is this bigger than that? Another way to say that is, by what factor does a change in the input relate to the corresponding change in the output? The derivative. Right? That's exactly one of our interpretations of the derivative. So G prime is the factor by which that size is stretched out to become that size. So you'll notice we have here delta x is G prime delta t. Okay, so altogether, notice how this works out. If we have if we start by looking at the integral on the right-hand side, we have some integral, on the x-axis, some integral f of x dx. We have some bounds. That's a Riemann sum. Everything in that Riemann sum, we just got to rewrite it in terms of t. This is that process that we just talked about. Just plug in. Don't forget that delta x is g prime dt. And now, by just moving some parentheses around, if I take those parentheses and just kind of regroup like that, notice what I get is a new Riemann sum. This is a Riemann sum in terms of t. I've got a new integrand. There's my delta t, which is going to turn into a dt, and it's literally an integral. Okay, so rewriting this as that gives me my substitution rule for integrals. Okay. All right, so there's 2 points of view that I want you to take away from what happened. One is that most of this is just plugging in. Right? It's easy to keep track of, so just remember that x is g of t. That literally just plug in. I mean, that's very straightforward. But 2 things you have to remember. One is how to rewrite the differential, and specifically, it gets stretched out. So the main thing you have to remember is when you do a substitution, don't forget to plug in this, what I like to call stretching factor, the factor by which a little piece of the t-axis got stretched out to make a little piece of the x-axis. Okay? So the derivative, conveniently, is the stretching factor. You've got to remember to put that in there. One way to say it. Again, this is just an alternative point of view from what you might have seen previously. The other thing is think about the bounds. These bounds become those bounds, and that's just a matter of observing that, based on this picture, we're taking an integral on the x-axis, on this interval, and we're just rewriting everything so that we can reinterpret it as an integral on the t-axis on this domain. So we're literally changing from this interval over to that interval. Given an integral here, I can plug in by g, and what results is an integral over here. So this is an example of a mathematical process that I think this looks a lot like. So I like to call this a pullback. That's the term. So the idea is the function goes that way. If you give me a number, if you give me a value, I can plug that number into the function, and out comes a value over here. But if you give me not a number, if you give me an expression, some expression in terms of x, then by plugging in x equals g of t and etc., an expression that was in terms of x effectively goes backwards. It gets pulled backwards through the function to become an expression in terms of t. Right? That's just how plugging in works. If you give me something that's in terms of x, and then erase all the x's and rewrite g of t, now you have an expression in terms of t. So plugging in pulls backwards through the function, you might say. So the term pullback, I think, is nice here. Okay, all right, so I want you to keep those in mind. Now we're going to talk about a two-dimensional version of this. And I'm going to start off by supposing that we're in the xy plane, and we've got some domain here over which we need to do a double integral. And let's just take a moment to recognize how unappealing this prospect is if I had to do a double integral in this domain, because you think to yourself, wow, my gosh, look at that. This is going to be ugly, because as I start to slice, come on, do a straight line. Pretend like that's a straight line. If you do your x slicing first, then you're going to have 1, 2, 3, 4 separate regions, right? Because you hit corners and you sideswipe edges and such, right? So you're going to have 4 separate regions on which you have to write down its own separate integral. And so you think, okay, great, well, let's slice the other way. Well, then you're going to hit corners again on multiple occasions, and again you have 1, 2, 3, 4 separate regions on which to write down separate double integrals. So yikes, unappealing. So what we're going to try to do is rip off the idea of substitutions, and we're going to try to view that undesirable domain that we have here, same domain. We're going to try to view that as being the image of some nicer domain, like a rectangle. And by the way, how to do this? I mean, how do you find this function? It can be hard, but there are situations where it works out. So for the moment, let me just say, let's pretend that we have this function. And how we're going to find that function, we'll deal with that in various examples that we'll see after we get our technique done. So for the moment, we assume we have this function. So we have this green rectangle over here. We have this purple function that if you plug in the green rectangle, out comes the blue undesirable domain that we had, that we're starting with, and that we've already decided, oh my gosh, I really don't want to have to work out the double integral on this purple blob over here. So the idea will be, if I have an expression, an integral, on this blue region, can I pull that back, just like we did for substitution? Can I pull that back and take this undesirable integral and rewrite it as an integral on this green rectangle? This is awesome. Rectangles, iterated integrals, bounds or constants. This would be a really nice integral to work out. Hardly any slicing effort. Okay, so that's the big idea. And roughly speaking, the answer is, yeah, go ahead. It's fine. No problem. Just plug in, right? I mean, don't forget, xy is g of uv. Anywhere you see x and y, this function tells you how to rewrite that in terms of u and v. Plug it in. No problem. The only issue being, what do you do with the differentials? Right? And so just like we had in the single variable case, there's the question of, given a little piece of the domain over there, by what factor does that get stretched out to become a presumably not the same, presumably different sized piece of this new domain over here? What's the relation between the size of this and the size of that? So here in this two-dimensional case, what we're talking about then is if I have some little rectangle there, delta u times delta v being the area, its image is going to be, well, I mean, gosh, exactly what? I don't know, it's hard to say. But its image is going to be kind of a parallelogram-looking little thing, depending on the nature of the function and how that function behaves. Presumably something kind of like a little parallelogram, like I've drawn here. And I want to know, what's the factor that I multiply by this area to get that area? That will be our stretching factor. And turns out to be a pretty straightforward calculation. Here's how it goes. Let's just recognize that the rectangle that we're starting off with is defined by certain vectors. That first vector, easy to write down. It's in the E1 direction. So it's a multiple of E1. The length of this vector, I've magnified for convenience. The length of this is our teeny tiny little piece of area. Because I wanted to be able to see it better, so I made it bigger. The length of that vector, the width of this rectangle, delta u. Okay, so apply the derivative transformation to it. Right, we have this g function. Apply the derivative transformation, and out comes the image vector. And there's a little bit of algebra to do here. There's this scalar factor of delta u that factors out. And then you see we have derivative transformation applied to a standard basis vector. That's a unit directional derivative. It's a partial derivative. It's the partial derivative of g with respect to u. Yeah. Oh, we're assuming that everything's differentiable. Yeah. That's a great concern. Absolutely. We have to assume everything's differentiable. Yep. Absolutely. Right. So, looking at that edge, we just computed what that is. It's gu du. And an analogous argument, if you look at this edge here, E2 delta v, apply the derivative transformation to that. That edge is gv delta v. So the area that we're interested in, the area of that output, this is a chapter 1 formula. The area is the absolute value of the determinant of the matrix whose columns are those two vectors that we just calculated. du du, gv dv. Right? So what I have highlighted in green here, that's just an old formula from chapter 1, right? If you have a parallelogram with two space, make a matrix out of them, take the determinant, don't forget the absolute value. Okay. And then a little bit of algebra. this factor of delta u factors out. This factor of delta v factors out. You note that what we're left with is exactly the Jacobian matrix. Wow, what a coincidence. What are the odds? That's exactly the Jacobian matrix of the g function. It's the partials of the output variables x and y with respect to the two input variables u and v. And notice we have our stretching factor now. The area of the output comes from the area of the input by way of multiplication by that factor. So this is the factor you want to make sure you remember. This plays the role of the derivative in the same way that when you're doing substitutions, calc 1, just don't forget to stick in a g prime. Right? G prime is the stretching factor that you have to kind of cram in there, otherwise, as opposed to just kind of substituting literally. Determinant, absolute value of the determinant of the Jacobian. That's the sort of two-dimensional substitution rule stretching factor. Okay, and so here it is. This is our change of variables formula for 2 dimensions. X and y are g of u. Missed. X and y are g of u and v. That's just plugging in. No thought required there. It's just a matter of just write what x and y actually are in terms of the given function, and then just don't forget that in rewriting the differentials, we have this stretching factor. Absolute value of the determinant of the Jacobian. So, works out very nicely. By the way, one little notational reminder, I guess, an alternative notation. Let's see. No, I guess I can't remember if have we used this notation yet? Forgive me, I've forgotten. I can't remember if I showed you all this before. I don't think I have. Okay, so this is a notational convenience to write partial. Let's see. Let me zoom so we can see that a little bit better. It's not letting me do that. It looks like a fraction. Partial, and then we write x comma y in the numerator, and the denominator partial u comma v. And the way you're supposed to read this is we're looking at the partial derivatives of x and y with respect to u and v. Well, of course, that's what the Jacobian matrix is. It's the various partials of the various outputs from G with respect to the various inputs to G. Right? So that kind of fraction-like notation turns out to be super convenient for the stretching factor you've got to take the absolute values. But the determinant of the Jacobian, very convenient alternative notation, because when you use that notation, when you plug in that for your Jacobian determinant, it's almost as if these cancel. Now, of course, they don't actually cancel. Right, here, let me do it over here. It looks a little bit better over here. It's as if those cancel. They don't actually cancel. This thing, despite our writing it as a fraction, is not a fraction. It's a determinant. Right? But it's a factor. Factors behave like fractions. So it's reasonable-ish to write it as a fraction because it behaves like a fraction, and it sure is convenient in the notation to sort of see it, at least notationally, actually kind of acting like a fraction. So anyway, I always feel a little bit weird when I do that because it's not really a cancellation, right? But the fact that it behaves as if the cancellation is okay is convenient. And again, somehow satisfying. I like to say it there. Okay. All right, so let's see some examples. Here's a wacky shape. Suppose I want to do an integral on that domain. And again, if you take a go straight at it kind of approach, you're going to hit that corner and that corner. thus giving you 3 separate chunks, 3 separate integrals, and that's triple the work, all else being equal. Prefer not to. You could try to slice the other way, same thing happens, you get 3 separate intervals. Okay, but I'm going to give us, now, how we find this function, again, talk about some examples of how you can, in some cases, it turns out to be kind of convenient. For the moment, I don't want to focus on that. For the moment, I'm just going to give us this function. We'll come back later to how to find it. But I assert that domain is G of this rectangle, unit square. So now that I've found, my highly undesirable domain, I see that it's the image of a much more desirable domain. Roughly speaking, I know how this problem's going to go down. Is I'm going to take the integral that I'm interested in over here. I really don't want to have to deal with directly. We're going to pull back through this given change of variables function. We're going to rewrite it as an integral over this domain, where the bounds are easy, 0 to 1, 0 to 1. It's the world's easiest bounds. Okay, so need to know what our stretching factor is. Don't forget, here's our magic formula for our stretching factor. By the way, make sure to memorize that. Super important absolute value of the determinant of the Jacobian. How do I find the determinant of the Jacobian? Well, here's the function. What are the partials of x and y with respect to u and v? So I've got 4 partial derivatives I have to compute here. Don't forget, this is partials with respect to u. Let me circle that a little better. Partials with respect to u. Don't forget, furthermore, the change of variables function is telling you x and y in terms of u and v. Right? So this is partial of x with respect to u, easily computed. This is partial of y with respect to u, easily computed. Likewise, this column here are the partials of x and y with respect to v. So partial of x with respect to v is 3. Boom. Partial of y with respect to v, 2v. Everybody happy so far? Okay. Take the determinant, blah, blah, minus blah, blah, and you get this absolute value of 4uv minus 9. Now, of course, at this point, you're thinking, oh, there's absolute values. How irritating. What do I do with these absolute values? Can I just kind of ignore? Can I just throw them away? Just kind of erase them? How important could they be? It's very important, as it turns out. You got to be really careful with this. So, what is this absolute value? What you're really hoping for is that the expression on the inside is either always positive, in which case you throw away the absolute values, or always negative, in which case you just throw away the absolute values and stick a minus sign on there. Right? What would be tragic is if this expression were sometimes positive and sometimes negative, depending on the values of u and v. That would be irritating, and then you'd have to chop up this domain into where is the absolute value, where is the object inside of the absolute value is negative, and where is it positive. Then you have 2 separate integrals, which is kind of what we were trying to avoid in the first place. Okay, so in this case, though, 4uv minus 9, what can I say about 4uv minus 9? And let me remind you, for the purposes of this question, I already know a bunch of information about u and v. And where I know information about u and v is here. That's telling me about u and v. This is my new domain over which I'm doing this new integral. This is telling me everything I need to know about u and v. And check it out. U is always between 0 and 1. V is always between 0 and 1. And with that in mind, u and v both being between 0 and 1, for uv is always less than or equal to 4. Therefore, for uv minus 9 is always less than or equal to negative 5. So it's clearly always negative. Right? So because it's always negative, its absolute value is the negative of itself. So there's our absolute value of our Jacobian determinant. It's 9 minus 4 UV. Does everybody follow that reasoning there? Okay. Right, so now plug and chug. Let's see here now. Step 1, let's rewrite x. How am I going to rewrite x? Well, don't forget x is u squared plus 3v. Right, so it's very importantly, when you got to remember this function g, that whatever your change of variables function is, that's telling you the output variables. In this case, x and y, in terms of the input variables. In this case, u and v. So x, the way I plug in, this is just the just plug straight in, no tricky curves here. Just plugging straight in directly. X is what the g function says it is. Along those same lines, what is y? Well, y is v squared plus 3u. Because g says it is. Right? So that's just plugging in. I didn't really do anything yet. Right? The moment of interest comes from rewriting the differential, dx dy. The big point is I have to insert my stretching factor being 9 minus 4 UV, as previously discussed. And we are done. We have taken an integral that originally was defined on this domain that we don't like, and we've now turned it into an integral on the unit square, 0 to 1, 0 to 1. Which of course we do like. Yeah, everybody happy? Questions? So this is a big win. I mean, so think about, instead of having this nasty domain, not only would we have to break it up into 3 pieces, but I'd have to figure out how to solve for y as a function of x on that curve. And how would I find y as a function of x on that curve? Here's my y and here's my x. And I don't even know can we do that? I mean, this looks like a nasty algebraic nightmare. Alternatively, though, rectangular integral of a polynomial, which is very straightforward. Okay, big win. Okay, next question. Here's another double integral I want to compute. My domain is a square with vertices at these locations, and so our domain is that this square. And again, if you want to, just put on the blinders and go plow head on into this thing, I mean, yeah, I guess you could, but your slicing is going to be a bummer because I wanted a different color there. You're going to slice through those corners if you do your dx slicing first. So 3 regions. You're going to go through those 2 corners if you do your dy slicing first. Again, 3 separate integrals. So that would be undesirable. So what I'd like to observe is that this square is a rotation of that square. Right? If I take blue and rotate counterclockwise by, I have to figure out what that angle is. That's just a little bit of trig. Just rotate counterclockwise, the blue one, you get the green one. So this function, this change of variables function that would turn the desirable blue square into the undesirable green square, it's just a rotation. And y'all might recall from section 3.1, we've already seen formulas for how to write down rotations. And so just as a flashback to section 3.1, this is the corresponding rotation matrix. So this is an example where you can find your own change of variables function. I mean, it's a highly specific and narrow instance. But if your change of variables is a rotation, you know how to write that down. Okay. Your Jacobian determinant, you got to do some algebra there, right? Details for you guys. The Jacobian determinant ends out being 1. Hope that's not a surprise. Again, keep in mind this Jacobian determinant is a stretching factor. So if you take some little rectangle and if you just rotate it, how much does that change its area? Well, it doesn't change its area. It just rotated it. And so it moved and it twisted, but it didn't change its area. So the fact that the stretching factor is 1 is highly expected. Now, you do still have to do the calculation, right? But this is what ought to be true. And then it's just a matter of plugging in. Again, don't forget that x is what the change of variables function says it is. That's just a matter of plugging in that formula right there for x that came from, we know how to rotate functions, we know how to multiply by matrices. Right, and likewise y also comes from the same information about the change of variables function that we already know. Okay. And so this undesirable integral there turns into this much nicer, actually really nice integral right there. Constant bounds, easy polynomial integrand. Not much to that one. Easy to compute. Yeah, everybody good? Okay. Hey, one more example I'm going to show you before we go on to a different thing. This is a strange one, but this is a surprisingly common scenario to come up. So imagine that you have a region that's defined by these two curves and these two curves. And so I have two green curves and two blue curves, you'll notice. And I'm interested in the region that is bounded between those curves. And it seems awkward and manufactured. This is actually a very plausible scenario. So I have memories of long ago when I was a college student taking a thermodynamics class. So if any of y'all are engineering majors, I think a lot of you are, you'll probably end up doing a calculation that's very much like a calculation I had to do once for an important thing of understanding the efficiency of something called the Carnot cycle, which in thermodynamics is a big deal. And the way you compute the efficiency of the Carnot cycle, and there's a lot of details that I'm not going to talk about, but you end up drawing a diagram that looks a lot like this. There's two curves with equations that look a lot like this, and another two curves with equations that look a lot alike, kind of like this. Different numbers. The exponent there is not a 2 exactly. It's something a little different. Whatever. And you end up needing to do an integral on this domain. So this is very, very pulled literally from a real application. So how do we do that? So we need to figure out some way, if possible, to take this highly undesirable domain that we're very interested in and view it as the image of a more desirable domain. And wouldn't that be nice if we could do that? So the tricky thing about this question is we're actually going to go the other way. We're going to relate by making an image of the ugly domain to be a nice, desirable domain. Okay. The choice of what this function is motivated by these equations. So here you see this xy and that xy. We're going to let u equal to xy. You'll see the y in just a moment. But this is. Let me just get it done first. We're going to let xy squared be v. So there's our function. Comes straight out of the equations that we're given. I observe that this function goes that way. You give me an x and a y, out comes a u and a v. Notice that this curve here, that blue curve, the equation is xy equals 6, or otherwise known as u equals 6. this weird blue curve over here, its image is a straight line over here. Right. And likewise for all the other lines. So that one is U equals 10. The other two are V equals 5 and V equals 7. So we've got this weird domain that we don't like, right? Its image is a very desirable domain that I do like, namely a rectangle. So we've kind of sort of done what we wanted to do, but it's sort of backwards, if you will. That's a little awkward. But it turns out that everything we need is here. All I've got to do is figure out how to take the integral that I'm interested in. I've got to use this backwards algebra to, well, just to try to figure out how to write x's and y's in terms of u's and v's. So I have to do a little bit of algebra with this function, maybe, right? I've got to figure out what the stretching factor is and how to use that backwards. But that's all going to work out, as it turns out. So here's the details. First of all, let's compute our stretching factor. Let's see, where did I put that? Here's the stretching factor. Determinant of the Jacobian. So you write down your Jacobian, the function h right here, h of xy is xy comma xy squared. Take the various partials, take the determinant, and it turns out you get v. Well, you get xy squared. And then that xy squared, you have to ask, that xy squared, how do I write that in terms of u and v? And luckily, it's easily seen to be v. Okay, now what do I do with that determinant of the Jacobian? Very importantly, remember that when you compute a stretching factor, you're computing the thing that you multiply by the input to the function, size in the domain of the function, to get resulting stretched out size in the target of the function. So that's telling me, in this case, keep in mind the function's going that way. That's telling me du dv equals stretching factor times dx dy. Du dv, so area in the uv plane is stretching factor I just computed times area in the xy plane. Okay, well I want the other one. I want it to go the other way, so you just solve for that, and conveniently then you get this. Really easy to do that. I'm just dividing by that Jacobian determinant. And so what you get is the stretching factor is just the reciprocal of the one you computed. It's very convenient. It's no big deal. Right. Okay. Then start rewriting things. Dx dy, reciprocal of the stretching factor times du dv. You've got to just kind of play around with it to figure out how to write x squared y cubed. What our original integrand was. How do you write that in terms of u's and v's? You have to look at what are u and v and play with it algebraically until you see what that is. It ends up being u times v. So it's not directly plugging in. You're kind of inverting the function, but that's just algebraic game, so I'm going to let y'all worry about that. And then, of course, those cancel. And you have your easy new integral on the rectangular domain, and that's easy to compute. All right, so this process here of observing that, when you compute the stretching factor the wrong way, really what that means is that the stretching factor, the direction you want to go, is the reciprocal of that. Here's another way of saying that. If this is stretching, well, the reverse of stretching is squishing, or stretching by a reciprocal factor. I mean, it's very kind of physically plausible, I think. And if you don't like the geometry of it all, then certainly that's that algebra is satisfying. So I want to write that a different way, though. So this formula here, this the reciprocal stretching factor. If you write this in terms of this alternative notation, there's the reciprocal of the stretching factor that we just computed. And then notice that even though I don't know how to write x and y as functions of u and v, if I could hypothetically write x and y in terms of u and v, this is how that would go down. And then you see what you have, that that's equal to that, or said differently, this notation that looks like a fraction behaves like a fraction. So you're very welcome, and I would say encouraged to use this notation instead of writing down, determinant, Jacobian. If you use this notation, it will keep track for you of whether you need to multiply or divide. The point being that you write it down whichever way makes the cancellation, air quotes, work. Okay. All right. There's a version of this in R3. It's really, really, really the same thing. I'm going to let y'all read through this section. I'll highlight the punchline real quick. But you can imagine, you might have some undesirable, wacky domain. Gosh, it takes a long time even to highlight this monster. Right? Wacky domain. Yeah, but if you can view that as being the image of a rectangle, then you can do a pullback. Nasty integral on a nasty domain. Pull back through your change of variables function. Nice integral over a box. The stretching factor ends up being the determinant of the Jacobian. Well, the absolute value of the determinant of the Jacobian. It's the same thing. It's just that now that Jacobian is 3 by 3 instead of 2 by 2. I encourage y'all to read through the details to see why you're computing the volume of a parallelepiped instead of an area of a parallelogram. You have 3 vectors to compute by way of the derivative transformation on these 3 vectors. It's really analogous. Okay. All right. Okay. I do want to spend a little bit of time talking about some related theorems. These are symmetry theorems. And I hope you all remember some of these from Calc 1 class. Do y'all remember this result? If you have a continuous odd function. Do y'all remember what an odd function is? So an odd function is a function where if you plug in the negative into it, then you get the negative output. So f of negative x is negative f of x. Let me write that down. Here it is. Yeah. Function's odd. The f of negative x is negative f of x. Odd powers of x, for example. Thus the name. Okay. So, nice fact. If you have a function that is odd, let me highlight with colors more thoughtfully. If you have an odd function, and note that we are doing an integral here, but it's an integral on a symmetric domain. So the bounds here are negatives of each other. You have negative a to a. It's not just some random a to some random b, right? The bounds are symmetric over the origin. Such an integral is always 0. No antiderivative required. No fundamental theorem of calculus required. Just 0. Super handy. And it's not hard to see why that is. If you have a, I'm going to draw a graph of this because that's convenient. Here's our symmetric domain. Let's see here. I guess that's fine. Our odd function. Function over here is doing the exact negative of what the function is doing over here, then this cancels that and you get 0. It's roughly the idea. So I hope that's something you remember, and if it's not something that you've seen before, then I hope it's something that makes sense. You can prove this with substitutions. So I'm going to show you some analogous theorems that sort of 2 and 3 dimensional versions of these. Now I have to define what do I mean by an odd function, what do I mean by a symmetric domain. A little bit of terminology I have to define. just to, for the to be able to have the conversation about the analogous results. But this is just some definitions. So I'm going to define what I mean by a reflection over a line. It's exactly what you think it is. If you have a line, then reflection over that line means that, like the mirror image. All right, so just to say it precisely, if you draw the line segment from a point to its reflection, the reflecting line perpendicularly bisects that line segment. Okay, but it's exactly what you think it is. Given a reflection, a set is symmetric over that line if a point is always in the set if and only if its reflection is in the set. So, in other words, if when you reflect the set over like this, it doesn't change. So, it's a very geometrically familiar idea of symmetry. Right? Again, it's exactly what you think it is. This is just sort of how you write it down. And with this idea of a reflection, we can define what we mean by a function having odd symmetry over that line. And again, this is a rip-off of the idea from single variable calculus. You put the reflection in, you need to get the negative value of the function out. This is totally like the single variable version. Any questions about these definitions so far? Well, turns out that with these definitions being made, we have an analogous theorem. If you're looking at a particular double integral, be careful. Particular double integral, if the domain is symmetric over a given line, and if the function has odd symmetry, so we're looking at a double integral, some domain, some integrand. If the domain is symmetric over a line, if the function has odd symmetry over the same line, that integral is equal to 0. And the idea is not terribly different. I mean, if you're looking at a symmetric domain, let's see, do I have a picture here? I guess I don't. Oh, shame on me. If you're looking at a, let's say you're talking about a line like this, and if your domain is symmetric over that line, as I've tried to draw this, right? And if the function has odd symmetry, well, the function having odd symmetry means that whatever's going on over here, the exact negative of it is going on over there. And you're looking at an integral that has terms over here and terms over there that are exact negatives of each other because the function's odd. They cancel, everything cancels, you get 0. Okay. It's just a two-dimensional version of the theorem we just saw. Okay. Let me show you how to prove this result. The proof is pretty straightforward. Here's the expression that we're interested in. Keep in mind the domain is symmetric, and so it is its own reflection. That's free. Here, let me do it like, let me circle this like this. This is a change of variables. If you notice here, I have an integral over an image domain. I can pull back to the original domain, which of course is the same domain. But anyway, that's the image by way of the reflection. And of course, you just plug in the reflected points. Don't forget your stretching factor. Reflections, of course, the stretching factor is going to be 1. And because the function is odd, f at the reflected point is the negative value. And so what we end up with then is that this integral is the negative of itself, and therefore the integral is 0. So it's real straightforward proof. The proof of the one-dimensional version of this that you might have seen in Calc 1 is just a morally identical, except that you use the substitution rule instead of what we did here. It's morally equivalent. Okay, there's a three-dimensional version of this as well. I'm going to let y'all read mostly about the three-dimensional version, but it's talking about reflections over a plane in space instead of reflections over a line in the plane. But analogous ideas of what does it mean for a solid to be symmetric and what does it mean for a function to have odd symmetry. Same ideas. Analogous theorem for triple integrals. Okay, couple of examples. Let's see these real quick. Suppose I want to compute a double integral, as we often do, of course. Right? Suppose that my integrand is x squared y cubed. Suppose that my domain is the unit disk in the xy plane. And let me draw a picture here. Whoops. So the unit disk in the xy plane. And the first observation I'm going to make is this domain D is symmetric. It's symmetric over a lot of lines. It's symmetric over the y-axis, for example. Right? If you do like that over the y-axis, nothing happens. It's also symmetric over the x-axis. It's also symmetric over that line and that line and that line. Any line through the origin, in fact. There's lots of lines of symmetry, right? Okay, so I want to talk about the x-axis. The fact that this function, this domain is symmetric over the x-axis. I can write down a formula for reflection over the x-axis. If you take any point, wherever you might happen to be, or let me do this in pencil. Any point where you might happen to be, the formula for finding the reflection of it, easy to see that the x-coordinate stays the same, right? But when you reflect that point, the y-coordinate, you get the negative of that y-coordinate for the reflection. So, thus, this formula here for the reflection. Okay, so this is clearly a symmetry of the unit disk. We've got a formula for the explicit reflection, and I claim that this reflection makes the function odd. Now we're going to look over here at the function. Here's our function again. And keep in mind what it would mean for a function to be odd. I would need for f at the reflected point to be the negative of the value of f at the original point. So I need f of the reflection to be negative f of xy. And this is a matter of plugging and chugging. So you take this formula for this reflection, that right there, the reflection of xy is x negative y. And plug that into here, do a little bit of algebra. Sure enough, as required, you get that minus sign. Right, so we have the conditions are satisfied. The domain is symmetric over that line. The function has odd symmetry over that line. 0. Answer is 0. Don't have to do any antiderivative, don't have to do any bounds, don't have to do some sort of a change of variables or something like that, just 0. It's a really cool theorem. Now, I want to put a little qualifier on that. I want to come back over to, here's our statement of our theorem. This is more of a warning, I guess. The dangerous landmine hidden in this statement. The domain symmetric over a line. The function has odd symmetry over the same line. Right? It's got to be the same line. The line of symmetry of the function, the line of symmetry of the domain. It's got to be the same line. If they're different lines, it doesn't work. Right? So the fact that maybe the function had odd symmetry this way, but the domain was symmetric that way, Doesn't matter. That's completely useless information. You cannot use the symmetry theorem. And here's why it's dangerous. It's so dangerous. If you apply, in this case where the lines of symmetry are not the same, right? If you say, oh, this integral is equal to 0 by symmetry because notice that the domain is symmetric like this and the function has odd symmetry that way, it's not a valid calculation, and nothing of what was written down is actually relevant to a actual valid calculation. So in other words, doing that, so misciting this theorem when it doesn't apply is not progress toward a solution. It's not like, oh, well, you were part of the way there and then you made a mistake. It didn't apply from the get-go. Right? And so it's almost impossible for a grader to give any partial credit if you misapply a theorem like this. So keep that in mind. I mean, if you want to apply this theorem, double check and make sure, oh my gosh, wait a minute, okay, am I sure? Okay, is this really reflecting the right way? Because it better be. And if I have this backwards, if I'm thinking about it the wrong way, nothing's right. Be ultra careful. Let me show you an example of how this can go wrong. That's this next example here. So you got this function. We have a domain that's a triangle with vertices at certain points in the xy plane. Let's draw that real quick. The vertices are, let's see, 0, 1, negative 1, 0, 1, 0. So our domain is that. And then you notice right away, you say, oh, hey, daylight, I see it coming. Look at this. We have a line of symmetry on the domain. The domain is symmetric over the y-axis. Oh, wait a second. We have an odd exponent. There's a cube there. This function's got an odd symmetry. And it's so easy to just get a little too symmetry happy and say, we have an odd symmetry on the function. We have a symmetry on the domain. Integral is equal to 0 by symmetry. And, you write that down, you walk away. And that would be worth 0 points, sadly, because it is absolutely invalid and it has nothing to do with an actual solution to the question. The reason it doesn't work is because they're different lines, right? So we've already drawn here the line of symmetry of the domain itself. But the function, this function, you notice the same function we were looking at over here, and it does have an odd symmetry, but it's a symmetry with that reflection, which is a reflection over the x-axis. So the line of symmetry of the domain, the only line of symmetry of the domain, mind you, and the only line of symmetry of the function, different lines. So there is no symmetry theorem that can be applied. And by the way, a real easy sanity check on this as well. Look at this function, x squared y cubed. On this entire green triangle, x squared is always non-negative. Y cubed, well look, y is always positive. That means that y cubed is always positive. This integrand is always non-negative over the entire domain. There's no way the integral could possibly be 0. Right? Okay, so heads up. Be careful. This is it. This one here, this example here, is what you might reasonably call a landmine question. And be careful. Okay. There's a few more examples. I'm going to let y'all read these examples. I do want to make one more quick comment, though, about how to use symmetry theorems on exams. By the way, don't forget we have an exam coming up in 6 days. Summer is so fast. It's ridiculous. I know. But, yeah. Anyway. Okay, so on the exam, if you cite symmetry as a justification for your computation of your integral, you do have to tell me certain bits of information. So with the following in mind. So here's a strategy that I used when I was in college. And I like to think that I dreamed this up myself. I'm sure I was not the first. But the strategy is this. Okay, if you don't know how to compute an integral, or if I've only got 2 minutes left and I don't have time to compute this integral, how about you just Hail Mary pass and just say equals 0 by symmetry, and then do other things, right? Because there's a chance you might be right. Right? There's 1 chance in 20, or I don't know, probably better than that, right? It's much better than 1 chance in 20. So related to that, I guess let me tell you another story as to why I think symmetry theorems are important. Right? So I did a second major in physics when I was in college, and so did a lot of integrals. No surprise, right? It's a big deal in physics, a lot of integrals. And my kind of back of the envelope, vague memories estimation is that about 20% or more of the integrals that I encountered in my physics major, about 20%, 0 by symmetry. That's a lot, right? So what we have here is a technique which, when properly applied, it effortlessly reduces your workload by 1/5. That's huge, right? Really big deal. So I scored on that several times. And, I don't have time to work this thing out. The integral equals 0 by symmetry. Gee, I hope that works. Came back, boom, points. Right? Okay, so now that I'm on the other side of the red pen, my goal, of course, is to understand, to gauge who really understands what's going on, right? And what I did, where I got those points on, physics tests where I didn't have time to actually work out the integral, did I actually demonstrate understanding of those integrals? No, I guessed and got lucky, right? That is not an accurate gauge of my abilities. If you're going to cite symmetry, ideally what I would like to see is you need to tell me what is the line of symmetry? What is the formula for the reflection? And directly confirm with the algebra that the integrand function is odd. So I want to know what line, what's the formula for your reflection over that line, and then just plug in and confirm the function actually is odd. Now there's a fourth requirement, and that is that you have to actually be correct. Right? So by which I mean, now you don't have to actually justify that the domain is symmetric. I'm happy for you to just say, come on, look at the picture, man. Right? That's fine. If you just assert the domain is symmetric, fine. Right? But you do have to be right. Right? I'm not granting you permission to just, make domains symmetric when they aren't. So if you misapply, if the symmetry in fact does not apply, then it's all complete garbage. Okay, so keep that in mind. Now we're going to revise this policy as we get a little further along. So roughly speaking, this would be a full justification for points. If the question says, hey, compute this integral, kind of like this example does, and if you want to cite symmetry, then I need to see all of that, right? If, on the other hand, the question was more of a, we're going to compute, we have this other problem here, and there's several terms pop out, and there's other things going on, and you're using a change of variables and blah, 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 and then at the very end, there's this integral that you have to compute, and you want to argue that, this integral is 0 by symmetry. You could be more terse there. In other words, if the symmetry argument is a tiny fraction of a much larger problem, then you can just say, for example, symmetry over the x-axis. Right? So, how much of this do I want to see is kind of proportional to how much is the evaluation of that integral a part of the entire question. If it's a small fraction of the question, I only need to see a small fraction of this. Okay. All right. Let's see. I have 45 seconds. Let's see. Give me 30 of those 45 seconds. I want to come. I just want to plan a thought. Right. We're not going to get anything done here, but plan a quick thought. It turns out, y'all remember polar coordinates. X is our cosine theta. Y is our sine theta. Right. if you think about it, this gives you x and y as functions of two other variables, and they're not u and v, but they're r and theta. There's nothing magic about u and v. Right? So we got two output variables, two input variables. You could interpret this as being a change of variables function. And it turns out that's crazy useful. It's hard to see it coming, but it's extremely useful. There are so many integrals that happen in the xy plane. Oh, the domain's a bummer. But if you do a pullback bipolar coordinates into the r theta plane, much more desirable. So I just want to plant that thought that we're going to reinterpret a coordinate conversion as a change of variables function. Details to come next time. All right, that took more than 45 seconds. Okay, see y'all later.